And we're back. This is part 2 of the introduction to RC circuits. And in this part we're going to have a slightly more complicated circuit. Instead of just having a capacitor and a resistor, we've now added a battery. I've labeled here the values of each component. So the resistor has a resistance R, the capacitor has a capacitance C, and then the battery has it creates a potential difference that's curly E, which is a way that you often see the delta V created by the battery written. It's sort of short for EMF, which again is short for electromotive force, which is a bunch of nonsense because it's not really a force at all, it's a potential difference. But, you know, for better or more likely for worse, that's what it's called. So this curly E is just, 9 volts, something like that. So let's analyze this circuit. We're going to assume that initially the capacitor is not charged. You can think about a different situation in which the capacitor has some initial charge. Right? I leave that for you to figure out. Let's analyze the situation as it is right now. So let's apply Kirchhoff's rule. Right? If the battery takes us up by, say, 9 volts, then the total voltage across here and the voltage difference across here is going to add up to 9 volts. If you go up 9 volts, you've got to come down 9 volts as we go around the loop. So let's write this down by Kirchhoff. Obviously the loop law, because there are no junctions here. We have that E, curly E, the potential provided by the battery is equal to the potential across the resistor plus the potential across the capacitor. Okay, so we can rewrite those. We know that the potential across the resistor is equal to the current through the resistor times the resistance, Ohm's law. And we could write that the potential difference across the capacitor is equal to the charge divided by the capacitance. That's the same as before in the first part. Now initially, right, there is no charge in the capacitor. So initially, this is 0. So that tells you that it's almost like the capacitor isn't there. Current's going to flow through the resistor. The voltage across the resistor, the potential difference across the resistor is just the same as the voltage provided by the battery. How can current flow around this circuit when there's a gap? Right, the capacitor isn't closed. Well, current's going to flow. It's going to build up here. We're going to get pluses on this side. I guess I'm going to add them now. Just that initially it's not charged. Those pluses, they're going to make minuses appear here because they get attracted. They come to the wire. They build up here. So the effect is that if they arrive, like pluses, if they were moving, would be arriving here and leaving on the other side. So the current is flowing all the way around. It's bridging the gap, even though no actual charges are jumping. Right? The charge arrives here, and it's kind of like a relay, where the charge arrives, the plus charge here leaves. The effect, though, is, as a result of that the capacitor is going to get charged up as time goes by. Right? The current is, of course, this way, through our resistor in this case, because this is the positive end of our battery. Okay, so in this case, because it's charging the capacitor, right, the current going through the resistor increases the charge. So we've got that Q I should write the rate of change of charge on the capacitor is equal to I. No minus sign this time, because the current goes towards the positive side of the capacitor, right? Little imagined plus charge moves, arrives here, starts building up. If 1 coulomb comes through here every second, well, then we're going to get 1 extra coulomb of charge here every second, so that's the rate of change of charge. initially not charged, so I guess we could write that Q at 0 equals 0, but it's not gonna stay that way. So Q is a function of time. This says at t equals 0. There's no charge. But that's going to change as current flows. And the moment we turn on the battery, say, current's going to flow because of the potential difference across the resistor. So let's put the pieces together, much like we did before. I'm going to plug this in here. And we're going to find that curly E equal to the rate of change of charge with time times R plus Q over C. Alright, I've just plugged this into here. This is just Kirchhoff's law, right? And our understanding of what the current does to the charge here. So this is true at all times, right? This is again true for any time this equation holds. This is a relationship between the rate of change of Q and Q itself. Because Q is the thing that changes with time. This is constant, and C is constant because they just are given by the the setup. So let me actually label those to make it clear. R is constant, C is constant, and curly E is constant. So the thing that's changing with time is Q. As a function, Q as a function of time. The charge in the capacitor as a function of time. So what do we have? We have a differential equation for Q as a function of time. It's a different differential equation from before, right? Because there's now this term over here. So let me rearrange this a little bit. I'm just going to divide everything by R and shuffle the terms around. And you can double check that if I do that, I can write this as dq dt equal to minus q over rc. It's kind of what we had before, but then as extra term, it's this. Right, so I just took this equation, divided by r, and reshuffled the terms of it. Essentially, I brought this over and took this one to the other side. So we ended up with this. Okay. So we also know that initially Q equals 0. So what we're going to call our initial condition. Right? So initially Q is 0. Initially the rate of change of charge in the capacitor is just the voltage over the resistance. Okay, that makes sense. That's consistent with what we know. Now, eventually, right, the charge is going to get bigger, and eventually this thing here is going to be equal to this thing here. And then the rate of change of charge is 0, and no more charge will flow. So we can, what I'm doing right now is I'm thinking about this equation. I haven't solved it yet, right? But I'm just doing some checks on what's going to happen. Does it make sense? So let me just do this. So at t equals 0, we said I've got Q equals 0. That was my initial condition. So that implies that dq dt, in other words, the current, is the voltage divided by the battery over R. That makes sense. At t equals late, the far future, sometime later, we might have that the charge gets bigger. You might find that Q over RC is the voltage divided by battery over R. In other words, Q over C is the voltage of the battery. If you think about this, it's just telling you that the voltage across the capacitor, Q over C, is equal to the voltage across the battery. No more voltage across the resistor, therefore. So, no more charge. dq dt equals 0. So we get no further charge. So we can kind of explore what this equation implies without actually solving it. Early on, it's, this is the rate of change of charge. Sometime later, maybe a very long time later, when it's kind of charged to a certain value that's given by this relationship here, well then it will stop charging, right? Because now the rate of change of charge is 0. But let's actually solve this equation in full. Again, I'm not expecting you to be able to solve differential equations, so I'm just going to state the answer. It's kind of my informed guess. I'm going to state the solution for all times, which we always care about. And the solution to this one is that Q as a function of time is equal to the voltage provided by the battery times C, and then it's not e to the something, but it's 1 minus e to the minus t over RC. And again, you can check that that is true, right? Check it now. And you want to check that this makes sense to you, so you understand what we're doing, right? We found a function that makes this equation true no matter what time it is. And actually do it, work it out. Okay, differentiate the left-hand side, plug it in here. You plug the function itself into here, you simplify, and hopefully you find that the left-hand side is equal to the right-hand side, and all the time dependence is cancelled out. So, emphasize, actually do this, right? You learn, you develop understanding by doing it, by working with this stuff. If you can't solve differential equations, you can check solutions. So let me put a function q against time. So just from our initial thoughts, right, we start at 0, at time 0, we knew that. And the slope here, the rate of change of q, where is it here, is just the curly E over R, right? The voltage that the battery provides divided by R. So I can't really draw this, but it has some initial slope. But a long time later, it stops charging when it's reached a certain value of q, and that value of q where it stops charging was given by, well, really if I simplify this, I can cancel out the R. I get that q is curly E times C. Let me make a little note here. Q is E curly E times C. Right, that makes this true. So it stops charging when Q is equal to the capacitance times the voltage provided by the battery. Now, if you actually plot this function, again, go to some app. I mean, say a good one is for example Desmos, the Desmos calculator, desmos.com. That's super easy to use, really pretty graphs. Go use it. Right, actually plot this function, plug it in. Pick some numbers for this, right? Pick some values for this. See what the graphs look like. Play with the numbers. That's how you get an understanding. Okay, so what it looks like, you'll find it looks something like this. You notice that as t gets bigger and bigger, this thing here gets closer and closer to 0, because e to the minus a big number is a very small number. So you get very close to this. For this to actually go to 0, though, we'd need t equals infinity. Right? And you can see this line here is going to approach this value asymptotically, but it'll never quite get there. But if you wait long enough, you're going to get really arbitrarily close to discharge, and that would be the charge in the capacitor when it's fully charged and no more current will flow. Now, we could think of all sorts of other setups, right? So here's a fun one to think about. I'm not going to solve this for you. That one is for you. Imagine I've got a battery, some EMF, curly E, and I'm going to have a resistor here, and a capacitor here, much like before. But then I'm going to put a second resistor in parallel. Imagine this is R1, this is R2, there's some capacitance C. What's going to happen? Again, assume this starts out not charged. You can imagine what happens. Current's going to flow, right? And initially there's no potential difference here, so it's almost like it's just this circuit here. But then we're going to start building up charge. We're going to get a potential difference, and the potential difference across here is the same as the potential difference across here. So that means we're going to get a current through this one as well. And the current that comes through here splits into two. Part of it charges the capacitor, part of it goes to the resistor. It's a little bit more complicated. Think about it very carefully. Write down the junction rule. Write down the loop rule. Write down, well, a loop rule here just tells you that the voltage across this is the same as the voltage across this. Put the pieces together. Current through this one is going to be the rate at which the charge on the capacitor increases. Put the pieces together. Going to get a differential equation. Can you solve it? I don't know. You can try. You can, do guesses. It's going to be somewhat similar to what we've had so far. What's going to be the very sort of, at time equals infinity, what's going to happen? Is charge going to continue to flow, or is it going to stop? Well, in this case, because part of the charge can go this way, right? It's going to keep going this way. Eventually, you're just going to have this big loop as kind of the only part that's still moving, and the potential difference across here is just the potential difference across here, which you get from just having a circuit with two resistors in parallel. Okay, this was a lot of information, a bit of a mouthful. See if you can make sense of it. It's a fun little example to do. If you can do it, you've really understood how to deal with RC circuits. Although to actually solve it in full, you're going to need to solve the differential equation, which you might not have done. If you have done it, if you have taken a differential equation course, you have no excuse. If you haven't, maybe you can make an informed guess, or you can look up solutions online, and there are reference texts, big chunky books that tell you solutions to all sorts of differential equations. See what you can do. It's a little bit of a research project, I guess. So this is your challenge. This circuit here. But I hope you're able to make sense of the two simpler ones that I showed you for sure, that you understand how to deal with them, and that maybe you can get started on thinking about differential equations. What do they mean? How are they relevant? We're going to meet them again, certainly in multiple places in Physics 163. So be ready. We're going to understand them better. They're not scary. Sometimes they're difficult to solve, but you don't have to solve them. You just have to understand what they mean, right? And if I give you a solution, well, can you check that I'm not lying to you, that it is actually a solution? Also, you're now in a good position to tackle the homework problems on RC circuits, understand a little bit more about how they work and how you get a time-dependent behavior. That's something you don't get for just normal resistor circuits. I'm not going to talk about them again. That's enough. Alright, have fun with them, and I will see you later.